Welcome to video 1.7. In this video, I'll be covering my method for approaching NMR spectra, introducing this thing I like to call the doorway method, and how you can use this strategy to avoid making incorrect assumptions and really add some structure to the way you approach interpreting your 1H NMR spectra. I've broken this process into 4 different steps, and I'll take you through it with a simple molecule, and then in the next video, we'll do 3 more complicated examples to show you the application of this method. The first thing to do is identify the formula that you're given. You must be given a chemical formula. And then calculate degrees of unsaturation. As a quick reminder, degrees of unsaturation will give us information about the number of pi bonds and rings in a molecule. It's a very useful piece of information to have handy when we're trying to build a structure, right? Once we've dealt with all our DOU, we know that we get to avoid any further double bonds. Or if I come with a structure that doesn't have the correct number of DOU, I immediately know that it's wrong. A good piece to cover right away. Right? Remember as well that if you have a DOU of more than 4, it's typically going to be a benzene. Now, the second thing we're going to do is copy all of the relevant information from that NMR spectra into a table. Remember that the goal is not to look at the spectra. The spectra is confusing. The information, right, the chemical shift of each signal, let's say that there's 3 signals, we'll list the chemical shifts, list the integrations, list the multiplicities, figure out the number of neighbors, right? Once we have this information in a table format, there's no reason for us to keep looking at the spectra, right? The only time I'd say you should look at the spectra once that information's in a table format is if you're concerned that you may have copied something incorrectly. Then you can go back to the spectra to make sure you didn't. Okay. One thing to do as well in this step is make sure that you sum your integrations and compare them to that initial formula. Remember that if you have to double them or triple them, that may be a sign of internal symmetry in the molecule, which is, again, a very useful thing to keep in mind if you're trying to solve that chemical's structure. Then, very nebulously, we're going to use the doorway method to build puzzle pieces. I'll talk about what that means. I like to call them puzzle pieces, but you may have heard this referred to as fragments of the molecule. And then, finally, use all the remaining information to connect the puzzle pieces and find the complete structure. Right? When you're given an easy NMR spectra for a smaller chemical, sometimes this first initial method might just solve the structure for you. But NMR is a complicated topic. Practice makes perfect with this technique. And sometimes we have to, eventually in step 4, really get creative, come up with ideas, test them, and try to make sure that we find a chemical structure that agrees with all of our data. Right, for harder structures, we're going to need even more advanced techniques than just 1H NMR, but that's beyond the scope of this course. So what is this doorway method? How does it work? The idea is to avoid any and all assumptions and build puzzle pieces, these things that we're very confident about, right? The biggest thing, and I can speak from personal experience when I've lost a lot of marks for NMR spectra when I made an incorrect assumption early and never checked it. Right? If you assume, for example, that your molecule has 4 double bonds with 4 DOU instead of a benzene, right, something that I did once during a lab final, you're never going to find the correct structure since the correct structure has a benzene. By avoiding assumptions, we can get as much information, as much known information as we can, and then make assumptions later once we have that information. One way I like to view this is imagine having a puzzle piece or a puzzle set with 100 different pieces versus take that same puzzle and kind of build them into 5 big chunks. Well, now you only have to connect those 5 pieces. It's a lot easier. So a doorway signal, this doorway method, means that you're going to start by only looking at signals that have an integration of 3, 6, or 9, right? Multiples of 3. The reason for that is that when you draw these out, these signals will only provide one direction to go, which is a little weird. Let's talk about it. Right? The idea is that we're going to lean heavily at the beginning on integration and multiplicity, less so on chemical shift. Right? Chemical shift is important, but remember from our earlier discussion, it can be misleading to look at a signal's ppm and immediately assume that it's got to be this thing. Right? That is kind of inherently an assumption, which we might have to do later. So what would it mean to have an integration of 3? Well, that's 3 hydrogens that are equivalent. That's going to be a methyl group. Right? A methyl group only has one extra connection that carbon can make, right, without violating the octet rule. So that's useful because if I tell you this signal has two neighbors, right, that means that it showed up as a triplet, right? Those two neighbors must be on this side of the molecule. You can imagine how, real quick, I'll just use this box. If I started with an integration of 2, and I told you that that same signal had two neighbors and was a triplet, you wouldn't be certain if those two neighbors were here, or if there was one on both sides, right? You'd be immediately starting to make small assumptions, and we want to avoid that at all costs at this step, right? So 3 integration is a methyl group. 6 integration can be very useful, right? Typically, one thing that you may see, and as I've been alluding to with my examples, is the isopropyl group, right? One way to get 6 integration is to have these 3 hydrogens be equivalent to these 3 hydrogens by rotation. The isopropyl group, by definition, will always have a hydrogen here, meaning that these signals would be expected to look like a doublet. That's a pattern that I want you to pick up on and apply when you're using the doorway method. If you see a 6H or a 6 integration doublet, that can be very strong evidence of an isopropyl group. Even better than that, we still only have one way to go, right? That's the idea of the doorway, that we're starting at the edge of the molecule and working our way in, right? When you walk through a house, through the door, you kind of have an idea that, you know where the entrance is, maybe the closet's to your left, you have an idea, versus imagine you're teleported into a random house in the middle, you might not know how to get out right away, right? So by starting at the edge of the molecule, working our way in, we can build these known fragments. The 9H integration is also useful, as it can really only be one thing, which is the tert-butyl group, right? 9 different hydrogens, all equivalent by rotation, right? This won't have any hydrogens here by definition, and these little pieces can be very useful. One thing to keep in mind is that an integration of 6 might also be represented by 2 methyl groups on both sides of a symmetrical molecule, right? Now they might be doublets, they could be other things as well, we don't know what they're connected to, right? Because of the overall symmetry of the molecule, they would still be identical. Keep in mind, though, that if there was overall symmetry, you would have had to double your integrations. Remember that if you double your integrations, that's sign of symmetry, and that might favor this idea when you're applying the doorway method with a 6 integration signal. Now that I've covered those basics, let's actually apply it for this simple spectrum. The chemical formula given is C2H6O, and with a molecule like this, right, there aren't even that many options, but let's just really apply this method with a simple structure. First, let's calculate the degree of unsaturation. As a reminder, that's 2C plus 2, the number of carbon, minus the number of hydrogen, divided by 2. Right? One thing you might want to remember is that there are some rare atoms that you want to keep in mind, right? If you have any halogens, you need to subtract them, like chlorine, fluorine, or bromine. And if you have any nitrogens, you're going to want to add them. That's from, again, the chemical formula. In this case, we don't have any of those atoms, so 2 times 2 is 4, plus 2 is 6, right? Minus the number of hydrogens is 6, divided by 2 gives us 0 DOU, meaning that we can eliminate the possibility of any double bonds, any rings, which helps us simplify things. It's just a good thing to do first, keep in mind. Now let's take this table and fill it in. So our signals, I've already labeled them from left to right as A, B, and C. The chemical shifts accordingly are 4, 3.5, and 1.7. Right? At this point, I'm not even really thinking about them. I'm just copying the information, being very careful not to make any mistakes. The integrations are 1, 2, and 3. And the multiplicities are a singlet, as A has 1 peak, a quartet, as B has 4 peaks, and remember that they're fitting that nice Pascal's triangle shape, and a triplet. Now a singlet, right, make sure if you forget here that a singlet, which is the smallest number of peaks, is going to represent the smallest number of neighbors, which is that. That reminds us that the relationship is -1 when you go from peaks to neighbors, meaning that the quartet will be 3 neighbors and the triplet will be 2. Right? This is basically all the useful information of the NMR spectra is now copied over into this table. So moving down, we don't really need the spectrum anymore. Let's remind ourselves that the chemical formula is C2H6O and that we have 0 degrees of unsaturation to work with. Now let's apply the doorway method. Looking at these 3 signals, and based on what I've mentioned previously, which signal do you think we should start with? I think the answer to that question is signal C. And the reason for that is that it has an integration of 3, right? 3, 6, or 9 are your doorway signals. So we start with signal C. Remember, the goal here is to make minimal or no assumptions, actually, when you're using this method. So what's going to happen? Well, we have a carbon. It has 3 hydrogens attached. These are signal C. That means that that carbon's got to be connected to one more group, right? And what else do we know about signal C? Well, we know it's chemical shift, but we're not looking at that at the moment, as we don't really know what it's connected to. It might be good to kind of note that it's a little bit low, but remember, that's not a huge deal, not part of the doorway method. The keyer idea, the more important thing, is that signal C has 2 neighbors. And since we used the doorway method, we know that those 2 neighbors must be connected to an adjacent carbon. Well, we've just kind of implied that there's a carbon here with 3 bonds, so there's one way to go. There's one more unknown thing connected. Before you move on, well, pay attention. We just did something that I like to call we've created implied hydrogens. I didn't really think about that. I was just doing the neighbors of signal C. But if these are hydrogens that are on my molecule, they should show up on my NMR spectra table. So I look at this, and basically the idea is, if I can guaranteed assign these to a signal, we can keep going. But if I have to make even the smallest assumption, I'm going to avoid that. At this point, this signal would be expected to have an integration of 2, as we have 2 hydrogens that are the same. Right? We're not entirely sure about the rest of the context, but with that, signal B is looking very likely. Not only does the integration agree, but the multiplicity does as well. Right? We don't know what's connected on this side, so we don't actually know how many neighbors these hydrogens have. But we do know that there are 3 on this side. So what I could say is that these 2 hydrogens have at least 3 neighbors. And that disqualifies signal A from contention, making signal B guaranteed they have to be these 2 hydrogens. Now signal B, we may notice a higher chemical shift, but again, something to notice, not really to work with at the moment. Right? We notice that it has 3 neighbors, which means that there are no neighbors on this side. There's no more coupling information, and that wraps up our puzzle piece. So by using the doorway method, I've almost guaranteed the existence of this ethyl group on my molecule. I'm not sure what it's connected to, but I know there's an ethyl group that represents signal B and C, which means that signal B and C, at least for now, are handled. All that leaves us with then is signal A. We check the table, and signal A doesn't have an integration of 3, 6, or 9. Keep in mind, you can do multiple doorways at the same time, or, in sequence before you approach the last step, which is finishing up. So for this part, one thing I like to do is do a bit of quick math, take a look at my formula, and see what I've dealt with in my fragments. Here, I've implied that there are 2 carbons, so I'll subtract 2 carbons. We've dealt with 5 of the hydrogens, but we haven't dealt with the oxygen yet. Once again, probably the hardest math you're going to have to do in OChem is addition and subtraction, at least at this point. So we're dealing with the fact that we have 1 hydrogen left over and 1 oxygen left over. Now, again, I told you it was a simple NMR spectra, and so this should be pretty clear that we're going to have a hydroxyl group connected here. Right? It won't always be this easy, but at this point, when you're trying to solve the remaining structure, that's when you would take a look at chemical shift, integration, other technologies like IR, other types of techniques to give us more information. But at the end of the day, we can come up with a structure. And the nice thing about NMR is that as long as you have the time, you can always check your work. I'm suggesting now that this unknown structure is ethanol. So let's take a look at the chemical shifts, right, and make sure that they agree. We see signal A at 4 ppm, which makes sense considering that it's directly connected to an oxygen. Now, keep in mind one thing about these OH signals is they can actually range quite a bit. If you look to most correlation tables, you'll see them in a range of somewhere from 2 to 6. They can be quite variable, right? One thing to note, though, as well, is that there is no coupling information through heteroatoms. So this oxygen, even though technically this hydrogen is 3 bonds away from B, we're not going to expect them to show up as neighbors. With that in mind, a chemical shift of 4 and an integration of 1 with a singlet makes a lot of sense for A. We've already verified that B and C make sense in terms of their multiplicity and integration, but let's look at their chemical shift to get even more certainty, right? A chemical shift of 3.5, well, that makes sense for B. After all, it is adjacent to an oxygen, which is de-shielding. Signal C being at 1.7, right? It's in that kind of close to that boring range. But yeah, it's 2 carbons away, or 1 carbon away, I suppose. 2 carbons away if you include this one, from that oxygen, maybe making it a little bit de-shielded. But these numbers agree. They're parsimonious with our data, with our structure. And so, yeah, when we have a structure that matches the NMR data, we have the correct structure. That's the beauty of NMR, right? Compare what we just did to an IR spectra that would show us a big OH peak, right? Much more informative, much more confidence. That's how we're going to approach NMR spectra. Hopefully you like this method. And let's now apply it for more complicated structures in the work along video to wrap up the NMR topic. I'll see you there.